Alrighty guys, we're going to go ahead and get started with our electrostatic force notes, and these ones specifically are talking about Coulombs Law. So what I want to talk about first are charges, and we can see here that we have a few charges. We have two positive charges on top, and then a positive and negative charge on the bottom. And we know that two charges of the same type will repel one another, just like we saw, and two charges of the opposite type will attract one another, just like I showed here. The two charges will experience a force pushing them apart or pulling them together. So again, we just saw that two positives pushed each other away and opposite charges pulled each other together. Let's talk about unit of charge. Well, we mentioned this in our last notes, and the unit for charge is just the coulomb. And the way we abbreviate Coulomb is with a capital letter C. The charge of an electron is negative 1.6 times 10 to the negative 19th Coulomb. The charge of a proton is the same thing except positive, so positive 1.6 times 10 to the negative 19th Coulomb. Both of these charges are extremely small, it's just that the electron is negative and the proton is positive. How much force? So the amount of force that two charged objects experience are going to depend on three factors, and this is really important. The first is going to be the charge on that first object, and we're going to refer to charge as like Q1, so object 1 has some charge, so we'll call it Q1. The next is going to be the charge on that second object, and we'll refer to that as Q2. And lastly, the distance between them. So when we put all this together, it actually gives us a really nice equation, and that's called Coulombs Law. And that equation on the left-hand side just says that Fe, meaning the electrostatic force, is equal to K. Well, K is the electrostatic constant, and we'll talk about what that is in a sec, times Q1, which is our first charge, times Q2, which is our second charge, divided by d squared. And d is referring to the distance between them. So like I said, that K stands for a constant, and that constant is going to be 9 times 10 to the 9th. And since it's a constant, it is a value that I will give to you every single time on every worksheet and every quiz and test. A really important thing to note though about this equation is that the distance on the bottom is squared, meaning that the distance is going to impact the equation a lot more than either charge will. So let's look really carefully at this Coulombs Law equation. And if we look at it, we're going to realize that it looks a lot like Newton's law of universal gravitation. Newton's law of universal gravitation has to deal with a constant, in this case big G, times m1, which is the mass of one object, times m2, which is the mass of a second object, divided by d squared, and d is referring to the distance from the center of one object to the center of the other. And that's the same d that we would use in our electrostatic force equation as well. And again, the universal law of gravity is just telling us what the force of gravity is between these two masses, where the electrostatic force is telling us what the electrostatic force is between these two charges. Both have an inverse square relationship between force and distance, meaning as the distance increases, the forces get smaller. And again, that's because distance is on the bottom of the equation, and it's also squared. The further apart these things are, the less force they're going to exert on each other. Gravitational force depends on mass, and Coulomb's force is going to depend on charge. Which might be stronger? So let's take a second just to look at this because I think it's pretty interesting. So let's consider two electrons that are 1 times 10 to the negative 6 meters apart. What is the gravitational force between them? Well, in order to do that, we need to figure out the mass. And then what is the electrostatic force between them? Well, to do this one, we need the charge. Luckily, these are just values that we can easily Google. So if we look at our equation, we see that K is 9 times 10 to the 9th. Q1 is 1.6 times 10 to the negative 19th. Q2 is 1.6 times 10 to the negative 19th. And these are electrons, So it should be negative, but because they're both electrons, I know that those negatives are just going to cancel each other out, so I just drop the negatives. Divided by d squared, and our d is 1 times 10 to the negative 6. So if we take a look at our force gravity equation now, we're going to see that we have g, and our gravitational constant is just 6.67 times 10 to the negative 11 times m1. Well, the mass of an electron is 9.11 times 10 to the negative 31st times the mass of another electron, divided by d squared, and d is the same in both cases. We do the math and we figure out that the electrostatic force between two electrons is 2.3 times 10 to the negative 16th, and the gravitational force is 5.54 times 10 to the negative 59th newtons. We can clearly see that the electrostatic force is a lot bigger than the gravitational force, meaning that the electrostatic force is what's keeping those two electrons apart. Therefore, the electrostatic force is much stronger than the gravitational force for small charged objects like electrons and protons. And that means that this force is what's allowing those electrons and protons to attract and repel each other. It's not their gravity that's pulling them together, it's their electrostatic force that pulls them together or pushes them away. Let's take a look at our first example here. What is the electrostatic force between these two objects? So charge 1 has a charge of negative 2 coulombs, and charge 2 has a charge of positive 2 coulombs. First thing I want to note here is that one of these is negative and one of these is positive. So I know that the force is going to be attraction, that these two objects are going to be attracted to each other. Next, I want to look at the distance, and the distance is going to be about 2 meters apart. So if we look at our equation, we have electrostatic force is equal to K times Q1 times Q2 over D squared. So if you're able to get to this part where you identify your charges and identify the distances, it's just a matter of plugging it into the equation and solving. When we plug it in, we get 9 times 10 to the 9th. I include the units in my equation now in the notes, but when you guys do it, I recommend maybe leaving the units off so you don't get too confused. So we get 9 times 10 to the 9th times negative 2 times positive 2 divided by 2 squared. And notice where I have all my parentheses, I recommend you guys put all of your numbers in parentheses too. When you solve, you find out that the electrostatic force between these two objects is negative 9 times 10 to the 9th newtons. Notice how it's negative here. That's really important. And the negative electrostatic force is telling us that these two objects are attracted to each other. Let's take a look at another example here. And this one says, what is the electrostatic force between these two objects? So this time we have two negatively charged objects. Object 1 has a charge of negative 5 times 10 to the negative 6 coulombs, and object 2 has a charge of negative 2 times 10 to the negative 6 coulombs. The distance between these is 5 times 10 to the negative 9th meters. Again, both of these are negative, so I should be expecting a repulsion. I would expect these two charges to repel each other. I write down my equation, and then, just like I said before, it's just a matter of plugging in our variables. We identified Q1, we identified Q2, and we identified the distance. So we plug all that into our equation, go ahead and multiply everything through, and then divide by the distance squared. We find out that the force between these two objects should be about 3.6 times 10 to the 15th newtons. Notice how this force is so much bigger than our last force, but one of the main reasons is that the distance is so much closer. This picture doesn't accurately reflect the distance because that distance is 10 to the negative 9th. So that's very, 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 very close together. Like we said before, because these two charges are negative and because our force is positive, it means that they're going to repel each other. So the main takeaways here, right, is Coulomb's law. We want to make sure that we're paying attention to our charges and our distance. Distance has an inverse square relationship with force. And that's it for our Coulomb's law / electrostatic notes.